So the equation y prime equals ay, where y is a vector with n components, a is an n by n matrix. Our assumed solution is y equals e to the lambda t times this x vector, which we can write in this form, that this equation will give us a solution for any lambda that solves the degree n polynomial we get from this condition. And each of those solutions gives us a different set of n linear equations with solution for the x1 through xn. We can represent those n solutions to the polynomial as lambda 1, lambda 2, etc. up through lambda n. And we'll mention again that I've said it, but let's see it in writing, that solutions can repeat in pairs. They may be conjugate complex numbers. They may be zero. And I haven't written it here, but they can repeat in threes or fours or any number of repetitions up to n, depending on the original equation. So if lambda 1 through lambda n are the solutions to this equation, we call these eigenvalues. And for given lambda sub I, where I is some number between 1 and n, for given lambda sub I, the equation a minus lambda I times x equals 0, and that 0 should be the 0 vector, not the 0 number, for reasons we've talked about. That solution, or this equation, then can yield an eigenvector, x sub I, with components x sub I1, x sub I2 through x sub In. That might be a little hard to read. I had to write it kind of small. But it's just a series of n numbers. It's a vector, column vector with n components. So lambda I gives us solution x sub I through this equation. And that's, lambda 1. If I is equal to 1, then we have vector, or eigenvalue lambda 1 gives us eigenvector x1, and then eigenvalue 2 gives us vector x2, and so forth up to x sub n. So we say that we have eigenpairs. An eigenpair is an eigenvalue and the resulting eigenvector. So we have eigenpairs lambda 1 x1 up through lambda n x sub n. Now recall that our original assumption was that y be of the form e to the t times our x vector. Having gotten a value of lambda and a specific x vector, that is one of our eigenpairs, well, each eigenpair then leads to solution, e to the lambda 1t x1 for eigenvalue lambda 1, e to the lambda 2t x2 for eigenvalue x2, etc. Now, the set of vectors x sub I, and this set just stands for the set of vectors for x1 through xn, where x sub I is just the arbitrary vector in this set. This set may or may not be linearly independent. We could, if we get repeated eigenvectors, we could end up with duplicate solutions here, which would ruin our linear independence. So that and other factors might influence whether this set is linearly independent. If, however, these are linearly independent, then it's going to turn out that this is a fundamental set. And let's think about why. Recall that this is a fundamental set if its Wronskian is non-zero. Well, the Wronskian is just the determinant of our psi matrix. Our psi matrix is just the matrix whose columns are these vectors, so that in the process of calculating the Wronskian, we're going to take the determinant of this matrix, Now, without proving it or otherwise validating it, simple fact that the determinant of something times x1 plus something times x2 plus something times xn, where these are column vectors, so that what you have is the same factor all the way through the first column. The factor e to the lambda 1t applies through the first column, e to the lambda nt applies through the nth column. I said I wasn't going to justify it, but every time you make a selection of the elements in the different columns to multiply, you're going to get the product e to the lambda 1t up through e to the lambda nt. All these numbers are going to, all these factors, e to the lambda 1t through e to the lambda nt, are going to appear when we make that selection. The result being that our determinant is going to be e to the lambda 1t times e to the lambda 2t times e to the lambda 3t, etc., up through e to the lambda nt. The product of all these e to the lambda I t's multiplied by the determinant of just plain old x1 through xn. And that's how I've written it here. Now, I've written, you know that e to the lambda 1 plus lambda 2, etc., times t is e to the lambda 1t times e to the lambda 2t, etc. Just by the laws of exponents, this is the same as what I just wrote, or what I just said. So that our Wronskian is just this multiplied by the determinant of our eigenvectors, x1 through xn. Now we're trying to show that if our eigenvector set is linearly independent, then this is going to form a fundamental set. This forms a fundamental set if the Wronskian isn't 0. Well, if these eigenvectors are linearly independent, then their determinant isn't 0. And no power of e can be 0. E to the anything times t is a positive number. Might be really big, might be really small, but it's never going to be 0. And of course you should understand that at the very fundamental numerical level. This means that if this set is linearly independent, the Wronskian can't be 0. And since the Wronskian isn't 0, this solution set is in fact a fundamental set, meaning that it's a linearly independent set of solutions and that any possible solution is a linear combination of these solutions. That is, then our general solution will be c1 times e to the lambda 1 x1 plus c2 e to the lambda 2 x2, etc., up through cn e to the lambda n xn. Now, we don't have a completely good test for when these eigenvectors will be linearly independent, but there is one case in which we know they're linearly independent. If the eigenvectors, if the eigenvalues are distinct, then the eigenvectors have to be distinct. And it's easy to see why that is, because if ax equals lambda 1x and ax equals lambda 2x for any given x, well, that can't be. If lambda 1 is not equal to lambda 2, ax might be lambda 1x, but if it's lambda 1x and lambda 1 is not equal to lambda 2, then for the same x, you're not going to get ax equal lambda 2x. Ax has one value. Might be this one, but it can't be both of them if these two eigenvalues are not equal. Now, where does this get us? Well, the eigenvectors are distinct. And if the eigenvectors for distinct, the eigenvectors for distinct eigenvalues are not only never equal to one another, but they are, it turns out, linearly independent. Now, it takes a little more work to prove that, but it's not difficult. So if these eigenvalues are distinct, it follows that the eigenvectors x1 through xn are distinct, and by the theorem we just proved, This is a fundamental set. These are linearly independent. And all the properties that we mentioned earlier occur. So if we have n distinct eigenvalues, we're pretty much home free as far as solving our system. If they aren't all distinct, things can get a little more complicated, and we'll see how that works out shortly. Returning to our original example, okay, and we just talked about that at the beginning of the preceding clip. In the case of our original example, we've got these eigenvalues and these eigenvectors. Of course, the eigenvalues are distinct, so we know the eigenvectors have to be distinct, and x2 is a vector, and need to put an arrow over that. Okay. The fact that our eigenvalues were distinct, we got lambda 1 equals 1, lambda 2 equals 7, those are distinct, implies then that this set of vectors, which is our x1, x2 set of vectors, is linearly independent, which then implies that the solution set we get by pairing up our eigenvectors with our eigenvalues with our eigenvectors is a fundamental set. And in the case of our original example, and we've seen this set a couple of times already, this does form a fundamental set with all the implications thereof. Now that we've covered most of the theory in the process of solving at least homogeneous systems, let's go on and do some examples. We've done one example. That's about the only example we've done this whole time that we've been talking about systems of equations. So let's do a few examples and see how things actually work out in the general case.